Good morning. In this lecture I will talk briefly about mechanics of material, and I will give brief introduction about what is the mechanics of material or strength of material, or we call it mechanics of deformable body. First I would like to talk about mechanics. What is the mechanics? A classical mechanic is a branch of the physics that deals with the behavior of the object and studies the motion of object under the influence of forces. Mechanics can be divided into three subcategories. So, mechanics can be divided into three subcategories. We call it deformable body mechanics, rigid body mechanics, and fluid mechanics. Deformable body mechanics, sometimes we call it strength of material. So another name, you will hear about that. It is the same thing, we call it strength of material. Or sometimes they call it mechanics of material. Rigid body mechanics can be divided into two parts. One of them we call it statics, another we call it dynamics. And fluid mechanics again is part of the mechanics, but in fluid mechanics our object, it is not in solid form. In deformable body mechanics and rigid mechanics, body has solid form, but fluid mechanics, body is not solid form, it is not in solid form. So, static, it is the first fundamental courses we have in engineering. Static, definitely you had previously. Static deals with forces acting on a body at rest. Dynamic deals with the study of forces and their effect on motion. In static and dynamic, both in these courses, our object can be a particle or rigid body. Particles means has very small size, so we can neglect the size. So once we call it particle, it means has very small size and it is like 1 point. So we neglect the size. But rigid body, it means has a bigger size. For example, if I look at this object I can neglect the size, so I will assume it behave like one particle. But if I look at bigger objects, like for example this, I cannot neglect the size, so I will call it rigid body. Rigid body means no deformation, zero deformation. Of course, in real life we cannot have rigid body, but in some object, because of the object has solid form and the force we apply on the object, it is small, so deformation is so small and we can neglect the deformation. So with good approximation, we can assume that kind of body or object is rigid body. So in the static, our object will be divided into two categories, particle or rigid body. If it is very small, we neglect the size, we call it particle. If it is big and we neglect the deformation is so small, we call it rigid body. In one rigid body, for example, if I have one rigid body, On rigid body, if I have 2 points like point A and point B, the distance between point A and B before applying external forces and after applying the external forces will remain constant. So there is no deformation inside of the object. In dynamic, again, we have particle and rigid body. But if we consider the deformation in an object, we should look at another course. We call it deformable body mechanics, or it is the same course. Sometimes they call it strength of material, or sometimes they call it mechanics of material. So, in summary, deformable body mechanics, it is very similar to the static, but here we will consider deformation. So, strength of material deals with forces and deformations that result from their acting on the material. For example, if you remember, in static course, if you have one simply supported beam, assume we have one simply supported beam like this, with one hinge support, another roller support. We call this beam is simply supported. The length, for example, is L. If this beam is subjected to concentrated load at mid-span, for example, load P. In static, if you remember, we find the reaction, for example, if this is point A, this is point B, the reaction here, the AY will be, if it is exactly in L over 2, we know the reaction will be P over 2, this reaction again will be P over 2, and this reaction, because there is no external horizontal load, is equal to 0. In static, we find only reactions and which are unknowns and internal forces in any section of the beam or any object. But in mechanics of deformable body, we will find deformation. You know, if we have one beam and we apply load, this beam will deform something like this. And after deformation, here we will have deflection. I show with delta. How much is that delta? How we will calculate that? That comes from strength of material or mechanics of deformable body or mechanics of material. Or if, for example, we have one rod, we attach to the wall this rod, for example, 2 meters, and the cross-sectional area, for example, assume it is square shape, it is 20 centimeter by 20 centimeter. If I apply load here, F, this load can have any magnitude. For example, assume we apply here 10,000 Newton force. What will be deformation? If I pull this rod, definitely I will have elongation. How much is this elongation and how we can calculate that? That in static we cannot calculate this deformation, and we need another course which we will call it mechanics of deformable body. For mechanics of deformable body, first you need to know static very well, because it is foundation for this course. If you want to learn this course very well, please go review static course. You should know static very well, because it is base or foundation for mechanics of deformable body. After knowing static very well, learning this course, it will be very easy, and you will see it is very similar to the static course. Here I would like to review the units a little bit. I will talk about units, different unit we will have, different force unit we will use. So let's review that. Of course, I'm sure you had in static, but in any kind of classical mechanic course, we need units for length, for mass, for time, and for force, you know force is equal to mass times acceleration. In international system or SI system, the unit for length it is meter, the unit for mass it is kilogram, and unit for time it is second. Usually we use another unit system, we call it British system or US customary system. In British system, length unit is feet, and 1 feet roughly is equal to 0.304 meter. It is good to know. Unit for mass it is slug. Slug is unit for mass in British system, or sometimes they call it pound mass. Pound mass. But slug we use for mass unit in British system, it is 14.59 kilogram. And unit for time in British system, it is again second. So these are unit for length, mass, time. How about force? The force unit in the SI system, it is Newton. What is the Newton? Newton is the force required to accelerate an object with a mass of 1 kilogram 1 meter per second square. So if we have an object, the mass is 1 kilogram, and we want to accelerate that mass with the acceleration of 1 meter per second square, we need 1 Newton force. How about another force unit in British system? This is in SI system. In British system, the unit for force, it is pound force. Of course, you will not hear pound force. Usually they will call it pound. But real right term for that, pound force. Pound force is the force required to accelerate an object with mass of 1 slug with the acceleration of 1 feet per second square. If you go to the market, for example, if you buy any kind of product, any grocery store, for example, you go to the Walmart, you buy 1 pound, 2 pounds meat. That is not this mass pound. This is force unit. It means pound force. For example, if somebody asks about your weight, for example, my weight, it is 200 pounds. It means force unit. Slug times feet per second square. You will hear in SI system or international system, if you want to buy product or if you want to report your weight, you will talk about kilogram. For example, you will tell, I am 100 kilograms or I need 2 kilograms of meat. So that is not this mass kilogram, that is 1 kilogram force. It is force unit. 1 kilogram force is equal to magnitude of the force gives 1 kilogram of mass, acceleration of 9.81 meter per second square. This acceleration is gravitational acceleration. So, if we multiply the mass to the gravitational acceleration, the unit for force, it will be kilogram force. But mostly they simplify that. They call it kilogram, they call it 2 kilograms, 3 kilograms. You should pay attention once somebody talks. For example, I need meat, I want to buy 10 kilograms meat. It means 10 kilogram force, not this kilogram. It is not mass. You know force is equal to mass times acceleration. Weight is again force. It is mass times gravity acceleration. You should know this. And other things maybe it is good I review here. We call it about density. What is the density? Density is mass divided by volume. We show with rho. Or gamma, we show unit weight. It is weight divided by volume. Weight divided by volume, we call it unit weight, because we know weight is equal to mass times gravity acceleration. If I divide both sides with volume, what I will have, instead of this weight divided by volume, I can show with gamma, it is unit weight, mass divided by volume, it is density times gravity acceleration. So what is the relationship between gamma, unit weight, and density? Gamma is always equal to rho times gravity acceleration. And you know here, for example, mass unit is kilogram. The volume unit, for example, it is cubic meter. Or weight unit, it is Newton. The volume unit is, again, cubic meter. So you can find the unit for the unit weight. Next, I review about equilibrium. What is the equilibrium? Once we talk about equilibrium, first we should know we are talking about equilibrium of what kind of object. We are talking about equilibrium of particle or rigid body. As I mentioned before, particle, it means no size. It is very small. We neglect the size. We call it particle. So, for equilibrium of one particle, we should look at which kind of space we are talking. If we are in two-dimensional space or 2D plane, if we have one particle, a small object, we neglect the size. We want to see how we can have this particle in equilibrium status. So in two dimension, we have two directions. We have x direction, we have y direction. If summation of forces in x direction is equal to 0, it means this particle will not move in the x direction. If summation of forces in y direction is equal to 0, it means this particle will not move in the y direction. So, if I have one small object like particle, if summation of forces on this object in x direction is equal to 0, this particle will not move in the x direction. If the summation of forces in y direction is equal to 0, this particle will not move in the y direction. So if it doesn't move in the x direction and y direction, we call it this particle in 2D space, it is in equilibrium. If we look at to the 3D space, in real life we are living in the 3D space. If we have one small ball like particle in 3D space, how many directions do we have? We have 3 directions. We have x, we have y, we have z. So, in order to have this particle in equilibrium, the summation of forces in the x direction should be equal to the 0. Summation of forces in the y direction should be equal to the 0. and summation of forces in the z direction should be equal to 0. So in 3D space, if we have this particle in my hand, I show this as a particle, assume it is particle, it is small, we neglect the size. If summation of forces in the x direction is equal to 0, this will not move in the x. If summation of forces in y direction is equal to 0, it will not move in the y. If summation of forces in the z direction is equal to 0, it will not move in the z direction. So again, this particle, it is in equilibrium. But if our object is bigger, so we cannot neglect the size. For example, this whiteboard, it is not particle, it is bigger. So what we should do, for example, this one, size is bigger. I will not neglect the size. So what should I do? Again, if I look at the 2-dimension, 2D space for in plane structure, assume I have object, the size is bigger. It is like rigid body. Again, in this space we will have two directions, x and y. If summation of forces in x direction is equal to 0, this will not move in the x direction. If summation of forces in y direction is equal to 0, this will not move in the y direction. But still, it is not in equilibrium. Why? Because maybe summation of forces in the x direction is equal to 0. So it will not move in the x. Summation of forces in y direction is equal to 0. It will not move in the y, but it can rotate. So it can rotate. If it can rotate, again it is not in equilibrium. So in order to prevent rotation, we need another equation. Summation of moment respect to one point should be equal to 0, 2. So, if summation of forces in the x and y is equal to the 0, object will not move in the x and y direction, but still it can rotate. In order to prevent rotation, if we put summation of moment is equal to 0, this object will not rotate anymore. So this object, it is in equilibrium in 2 dimensions. In 3 dimensions, so in 2 dimensions, for equilibrium of one rigid body, we need 3 equilibrium equations. In 3D space, if we have one object in 3D space, it is like rigid body. In 3D space, we have x direction, we have y direction, we have z direction. In order to prevent to move in the x, y, z direction, I should put summation of forces in the x direction is equal to 0, summation of forces in y direction is equal to 0, and summation of forces in z direction should be equal to 0. But again, this rigid body can rotate respect to the x-axis, respect to the y-axis, and respect to the z-axis. So, summation of moment respect to the x should be equal to the 0. Summation of moment respect to the y should be equal to the 0. And summation of moment respect to the z again should be equal to 0. So, for equilibrium of one rigid body in 3D space, we need 6 equilibrium equations. Summation of force in the x direction is equal to 0. Summation of force in y direction is equal to 0. Summation of force in z direction is equal to 0. These 3 force equations will cause this object will not move, but still it can rotate respect to x, respect to the y, respect to the z. In order to fix it at that point and prevent rotation, summation of moment respect to x should be equal to 0, summation of moment respect to the y should be equal to 0, and summation of moment respect to the z should be again equal to 0. It is good I review what is the difference between force and moment. Of course, in this state, you should know what is the difference between moment and what is the force. But let's define one more time, and we will look at two different type of the forces. It is good again I review it. We have two different type of the forces. So we have contact forces. Contact forces and non-contact forces. What are contact forces? For example, if we push or pull an object, we apply normal to the surface that force usually. So contact forces can be divided into normal force, normal to the surface, or tangent to the surface. Tangent to the surface, if force is tangent to the surface, we call it shear force. If it is normal force, if it produces tension inside of the object, we call it tension force. If it creates compression, we call it compression force. How about non-contact forces? We have different type of non-contact forces. In physics, you know. Non-contact forces, for example, can be gravitational forces. Or it can be electrical forces. So, electric forces. Or it can be magnetic forces. Of course, we have other type of non-contact forces, such as strong nuclear forces, or weak nuclear forces. These are non-contact forces. Most forces we will talk in the static, dynamics, and mechanics of the formable body. They are contact forces. Of course, we will look at the gravitational forces too, but we will not look at these forces usually. Maybe in some special cases we need to consider, but in our topic, in undergraduate courses, we will look at these courses. Again, contact forces, it can be applied in very small dimension. If we apply force in very small dimension, we neglect the size of that area and we model it as a concentrated load or point load. So like F. Or it can be applied to one surface. For example, if we have snow or rain, the weight of that snow or rain is on one surface. So this is kind of distributed load. Distributed load, it can distributed in one area, for example, if it distributed load will be distributed in one area, the unit will be Newton per meter square. If it is concentrated or point load in SI system, it is Newton, or it can distribute it in one line. For example, uniform load on simply supported beam. This type of load, so we apply to one line. Of course, in reality, if the distributed load in one area, it is uniform in this direction. For example, this direction is L. The intensity of the load, for example, Q times L, because it is uniform in the L perpendicular to the board, I can convert to the line distributed load and show the intensity of the load with W. So this is about different type of the load we will have in these courses, especially in strength of the material. Let's see what else I should talk about. Okay, what is the difference between moment and force? The turning effect of the force, we call it moment. So the turning effect of the force applied the body is called moment. For example, assume we have one bolt like this. I use one rand in order to open or close this bolt. Okay. Here, if I apply force F at point A to the rand, what will happen? This rand wants to rotate this bolt. So, how it wants to rotate? Force times to the distance up to centroid of this bolt. If I show with D, force times D is tendency to rotate that bolt. We call it moment. So moment is tendency to rotate an object. If we apply force to one object, for example, I apply force to this object, what will happen? This object will move in the direction of this force. But if I apply force here, force times the distance up to centroid of that bolt, it is tendency to rotate that bolt. We call it moment. So, moment is equal to the magnitude of the force multiplied by the perpendicular distance between its line of action of the force, and the axis of rotation. So the unit for moment, it is, for example, if the unit for force it is Newton and unit for the distance it is meter, will be Newton times meter, or if force unit is pound and distance unit is feet, it will be pound feet. This is moment. We have two different types of the moment. Later on we will talk about those. We have bending moment and twisting moment. So moment can be divided into two categories again. So moment, we will have two different types of the moment. Moment will be divided to bending moment and twisting moment. Twisting moment, they call it torque as well. So there is a similarity and difference between these two moments. and on different chapter we will talk about what is the bending moment and what is the twisting moment. I think it is enough for introduction part, and we will continue next session. Thank you so much for watching this lecture. See you next session.